Okay, so in this hour, I kind of want to give a idea of the current things that are happening in Lean and the future directions that people are exploring and that can have very important implications for the future of mathematics. So where we are and where we are going. And I'm going to revisit some of the stuff that Sander already talked about in the first hour that we saw yesterday. So let me tell you about MathLib today. So if you recall, MathLib is a Lean formal library of mathematics, and right now is one of the fastest, if not the fastest, growing library of formalized mathematics. It now contains almost 2 million lines of code and has contributions by more than 500 contributors. And in MathLib, you can use freely classical logic and the axiom of choice. So this differs from other systems that prioritize a more constructive approach, but MathLib uses classical logic and just the axiom of choice freely, and it also prioritizes abstraction and generality. So theorems try to be stated in as much generality as possible. So this is an example of a theorem that you encounter in the Lean library. Let me click on it and show you the documentation page. So here it is. This is Fubini's theorem, which says that you can integrate over a rectangle by iterated integrals. And you might encounter this theorem using the Lebesgue integral, and if you're dealing with continuous functions, the Riemann integral. But here we see that this is defined using the Buchner integral, which, well, at least I was not familiar with before this. And this integral takes values in a Banach space. So you can see how, well, the theorems are stated in maybe more generality than you are used to. So let me tell you how MathLib is built, or how people contribute to MathLib. So in principle, anyone can make a pull request to the MathLib repository on GitHub. So if you are unfamiliar with what a pull request is you are some changes that you make to the code that you would like to see merged into the repository. And in principle, anyone could make a pull request. But then a MathLib maintainer will look at what you've written and will either approve or by some iterations get to something that might be included into the library. So if you want to contribute something to MathLib, you need to follow certain guidelines regarding style, code location, naming conventions. So just to give you a brief idea, here are some style guidelines that must be followed for MathLib contributions. So variable names and line name and so on. So when you submit or when you make a pull request, your request will be reviewed by a MathLib reviewer, which is a MathLib or Lean user that has experience contributing to MathLib. So they will review your code and they will maybe comment stuff about it. So if they don't like something, or if they would like to see an improvement, or if they don't think it really fits in MathLib, they will say that then. And then after this, maybe back and forth with the reviewer, MathLib maintainer has a final say about what gets merged into the library. And well, there are many people, and these days, a lot of people are getting into Lean. So there are a lot of pull requests, a lot of people trying to contribute. So these can create backlogs and delays. So the median wait time is around 2 weeks, but this can be way more than 2 weeks And this is one of the bottlenecks for the growth of MathLib, the labor that it requires to review all of these pull requests. So there is a program called the MathLib Initiative that employs some people to streamline this process, so to make this reviewing process faster. And here is the review queue of MathLib. So here you see a list of the pull requests created by anyone. And we can see here the total time in review. So for example, this one has been in review for 56 days. And you can see here the MathLib reviewer that has been assigned to this particular pull request. And right now there are 191 PRs waiting for, waiting for this cycle to end. So I can click maybe on one of these and show you, well, this doesn't say much. But usually here you see the comments, the back and forth between the author and the reviewer, so that it gets hopefully finally merged into MathLib. By the way, if you have any questions, please stop me.
Is it at all possible that somebody could make a bug by, say, not dealing with the natural numbers properly and having 0 minus 1, and then you'd have the theorem in there that's actually not be there?
So that's a very good question. So everything is carefully reviewed by the reviewers to avoid, for example, someone introducing a weird notation that kind of makes it look like you proved something that you actually didn't, or you're not using the right MathLib definitions. And so, yeah, the statements are carefully checked by the reviewers.
Human check.
Yes, human check. But the code itself, the fact that it type checks, is done automatically. So Lean checks the proof, only proofs that type check are allowed into MathLib. So you know that everything that is in MathLib type checks, but the reviewers do check the statements. Yes, so this is human checked. Okay. So now let me say something about modern formalized results. So we saw already that it can be quite painful to maybe formalize some basic stuff, and that might make you think that, well, it would be really hard to then formalize more modern mathematics. But some modern mathematics has been formalized. The thing is, if you want to formalize something, well, you need to formalize all the theorems on which that thing depends on. So it takes a while for the library to become big enough to be able to even state some of the modern mathematics results. But let me say something about a project that Sander mentioned called the liquid tensor experiment. So this made it into the news. So Proof Assistant makes jump to big league math. Mathematicians using the computer program Lean have verified the accuracy of a difficult theorem at the cutting edge of research mathematics. So this article is talking about the liquid tensor experiment. So in December of 2020, Peter Schulze posted a challenge in Kevin Bussard's blog. And the challenge, it was for the formalization, for the Lean formalization community, is to formalize essential theorem in an area that he's been developing called condensed mathematics. And this is a fundamental theorem in liquid vector spaces. So Schulze said that the proof was, well, it required a bunch of technicalities and very technical computations. So he wasn't completely certain that it was correct. And he wanted to have that certainty. So he says, it's some very convoluted thing with many moving parts. It's hard to know which parts move by how much when you shift one of these parameters. So he wanted to have the certainty that this thing is correct. And well, a great way to do it is to try to formalize the statement. So he posed this challenge to the Lean community. And in July 2022, the liquid tensor experiment was completed. So 1.5 years after the challenge was posed. And turns out that the proof was essentially correct, modulo some slight imprecisions that were found during the formalization. And so Schulze says, well, one day I was sweating a little bit. There was this issue about an infimum being actually a minimum, and one needed to prove that, but on paper this wasn't, well, one didn't notice this thing. So these small things came up during the formalization process. And Schulze did not directly formalize, but he was in constant communication with the people during the formalization. So here is the formal statement of the theorem that I showed you before. Maybe I will go back and now forward, and you see that it does resemble the informal description. This project was led by Johan Kommelin, and as I mentioned, it involved efforts of multiple members of the Lean community. And then, so in another post in this blog by Kevin Buzzard, he's asked, what else did you learn? Well, what actually makes the proof work? So this experiment changed his impression about proof assistance. This has changed drastically my impression of how capable proof assistants are. I now think it's sensible in principle to formalize whatever you want in Lean. There is no real obstruction. So this was a very important moment for the Lean community, and also it made it into the news. So it was a big deal. And this is not the only example of modern formalized results. So some of this stuff Sander already mentioned. So for example, the formalization of the solution to the capset problem, or well, this one wasn't mentioned, but so there's this conjecture that was made by Erdős and Graham, and Thomas Bloom proved it in 2022. So the conjecture is, if you have a subset of the natural numbers with positive density, then you can always find a finite subset such that the sum of the reciprocals equals 1. So this was proven by Thomas Bloom and submitted to a journal, but it was also formalized by Bloom and Babik Mehta, and they formalized the proof before they got the referee report. So they knew that the proof was correct before a human reviewer verified or checked the paper. There was also this project, the sphere aversion project that Sander mentioned. And right now, people are working on formalizing one of the results about packings in dimension 8. So this was a result by Marina Biasowska, who won the Fields Medal in 2022, if I remember correctly, because of this result. And right now, people are actively working to formalize this. So, yeah, I've mentioned the library and modern mathematics being formalized, but one of the perhaps most exciting things about Lean and digital mathematics is that it can allow for large collaborations to happen. So historically, math papers do not have many co-authors. So maybe 2 or 3, but not many. And the reason, well, one of the reasons perhaps is that everything has to fit together very exactly. And you need to trust your co-authors because error could make the whole thing crumble. So this makes collaboration, large collaboration, hard. However, with formalization and with Lean, well, this is not longer the case. You don't need to trust your co-authors in the same way, because you can trust the system to have checked the result for you. So in this way, also the fact that it's a digital system allows people from different parts of the planet to collaborate on the same project. And in principle, you don't need to know them, or you don't need to know their background or their credentials if they submit a proof that is type checked by Lean. So this also can increase the access to participation in mathematics for people that otherwise do not have, or the networks or the resources to be included in this level, research level mathematics. So here, let me show you some examples of some projects with large collaborations. So in launch in September 2024, there was the equational theories project, and this was led by Terence Tal, and it was completed in April 2025. And the point of this project is to map out the implications between equational laws in magmas. So magmas are a set with a binary operation, and that's it. And you can have, well, laws like the associativity law, for example, in a magma, but a magma does not need to have that law. And then Tao was wondering, well, which laws imply other laws? So yeah, for example, in the trivial magma, you have for every x and y, x equals y, and this will imply a bunch of other laws almost trivially. But you can construct a graph of all the magma laws that you might want to consider, and then draw an arrow if one implies the other. Yeah. So mapping out the thoughts of creating this graph was the goal of this project. So in this project, they consider magma laws that involve at most 4 magma operations. And it turns out that this results in 4,600 something equational laws. So this meant proving or disproving 22 million implications between these equational laws. And this project was completed, and everything is now formalized in Lean. So every implication or a proof of the or a disproof is formalized in Lean. So the counterexamples are formalized. So let me show you an example of one of these implications. So is this big enough? Should I make it bigger? So every equational law has a label, a number. And for example, the law x equals y, and this is for every x and y, x equals y. So this is just a trivial magma, doesn't say much, but then you can see this well, sequence of implications. So this equational law implies this one, and so on. And you can see the Lean proofs. So here it is. So equation blah, blah, blah implies equation this one. And you have a Lean proof. So this you can find for all of these implications. Okay, so let me tell you about an ongoing project, which is to formalize a proof of Fermat's last theorem. And this is being led by Kevin Bussard, and it was launched in April 2024. So the aim of this project, as I said, is to formalize a modern version of the proof of Fermat's theorem. And what Kevin Bussard is trying to do is, in 5 years, he wants to reduce the problem to results that were known in the 80s. So the idea in 5 years is not to formalize everything down to the axioms of mathematics, but just to results that were known in the 80s. And so he says, I will be able to explicitly state the results I need in Lean and pass them on to others. The beauty of the system, you do not have to understand the whole proof of FLT in order to contribute. So now let me say something about how these contributions work. So what Kevin did, and in general in these large projects, what people do is they break down the theorem into a bunch of smaller lemmas. And this is called a blueprint. So there are a bunch of results that together they imply the final big theorem. And then people can claim some of these lemmas and will say, I want to prove this lemma, or I want to prove that theorem. And then people work on those theorems or lemmas, and then they make a pull request to the GitHub repository. And that's how things slowly build up. And that's how you end up proving a very big theorem by proving small lemmas that people can contribute to. So to visualize and organize this process, there is this software that Patrick Massot created, which is for creating these blueprints that enable large-scale collaboration. So let me show you. This blueprint looks very innocent. This is a very big theorem, Fermat's theorem, and the blueprint seems rather small. So you can see, some theorems here, for example, maybe it's too small. It says, if there is a counterexample of Fermat, then there is a counterexample of this form where the exponent can be chosen to be prime. So this theorem, is already proven. This is easy. So here it is. This is a theorem, this is a proof. Okay, so those are easy to prove. And you can see the ones that are dark green, those are already stated and proven completely. So those are not the hard part. Also, for example, Fermat's theorem for exponent 3. This is also proven in Lean. This is the hard part. So if you have a counterexample to Fermat's theorem, then you can create something called, in this case, it's called a Vrije package, which is just this package of numbers, which is a counterexample to Fermat's theorem. And then using a Vrije package, you can construct an elliptic curve called a Vrije curve that is defined like that. Maybe it's too small. Is it too small? Should I make it bigger? No. And then the whole point is to prove that this thing cannot happen, so that actually a Vrije package cannot exist. And the proof relies on two big results. So there's a theorem by Mazur, which was known in the 1970s. So for now, the project is not focusing on this result. And then there is a big theorem by Wiles. And this one is the main focus. So every other chapter in this blueprint is about the ingredients that are needed to finally prove this big theorem. So if I go to chapter 10, for example, you can see what I mentioned. The proof is broken down into small lemmas. So lemmas and proofs, and definitions, and lemmas and proofs. And then we can see the graph corresponding to this chapter. And well, now you can see visually what's going on. These theorems are stated and proven, but they depend on stuff that hasn't been proven yet in MathLib. So this, if you look at everything that needs to be proven, is actually MathLib. And yeah, people are working on that at the moment. So now let me tell you about what I do, which is verified computations in Lean. Well, let me precisely tell you what I do, and then give you other examples of how you can verify computations in Lean. So already we saw last week that some of the main computational tasks of algebraic number theory are, if you have a number field, you might want to compute an integral basis, z basis for the ring of integers, or the discriminant of your number field, the class number and structure of the class group, or the unit group. And we saw some ways to compute this using ParisGP, for example. And these computer algebra systems are great. They are, very involved algorithms have been implemented in these computer algebra systems. Many people have worked to make them as optimal as possible, and they are reasonably, well, as fast as they could be, probably. However, as in any big piece of software, there might be bugs. So with a computer algebra system, we don't have a formal guarantee that it will always give the correct answer. So what could go wrong? Well, at different levels, different things could go wrong. So for example, maybe the algorithm depends on some mathematical theorems, and maybe those theorems are wrong. Or maybe the proofs that we know are wrong. Or maybe there's an edge case that is not considered, and it doesn't work every time. Maybe the algorithm itself is not correct. Maybe it doesn't compute what you claim it computes. So maybe your proof of correctness of the algorithm is not quite correct. Or maybe which is perhaps the most likely scenario, there are bugs when people are implementing the algorithm in different systems. So there might be bugs in the implementation or in other dependencies that you're relying on. So, yes.
Why set theory is correct?
Sorry?
Set theory is correct.
Set theory?
Yeah.
Is it correct?
Yeah.
Well, it's not neither correct or incorrect.
Yeah,
Yes.
because the state you started from one step before that what should be said. If I want to be complete, if set theory is correct, then
yes, okay. Yeah, if you assume, but okay, I'm assuming the logical framework is dependent type theory plus some extra axioms. If you take that for granted, yes. So my basis is some logical foundation. So computer algebra systems are efficient, but we have no formal guarantee of correctness. And proof assistants are slower because everything is checking the logic every time. But we have a greater guarantee of correctness. So my work is to try to verify some of the computations in algebraic number theory in the Lean proof assistant. So an example is, suppose some computer algebra system tells you that the ring of integers of a number field is given by this explicit basis. So I want to prove in Lean that indeed, say that ring O, which is the thing that the computer algebra system told me, is indeed the ring of integers of a number field. So Lean already knows what the ring of integers of a number field is. So the way it is defined in MathLib is the ring of integers of K is the integral closure of Z in K. And if you unfold that definition, what is the integral closure? Well, it's those elements in K that are integral over Z. And what does it mean to be integral over Z? Well, it means that there exists a polynomial over Z that is monic, and that when I evaluate my element at that polynomial, I get 0. So that's maybe different notation to what you're used to, but that's what I'm saying here. So MathLib knows the theoretical definition of the ring of integers. So what I want to do is, if I have some subring that I know explicitly, I want to be able to construct a proof in Lean of the explicit ring being equal to the ring of integers. So I want a formal proof that is checked down to the axioms of mathematics of correctness of such a computation. So together with Sander and Anna Bannon, we verified some of these computations of the ring of integers and discriminants of number fields. So here's an example of a number field. So K is obtained by adjoining a root of this polynomial of degree 4. And then we can actually prove in Lean. So O is explicitly constructed, and we can actually prove in Lean that O equals the ring of integers of K. And we can prove in Lean that the discriminant of the number field equals this explicit number. So these are all Lean proofs. And in this way, we verified some of the entries in the LMFDB, the L functions and modular forms database, which has some data about number fields. And we can also formally certify other invariants, but these are way more computationally expensive. So for example, we can give a formal proof of the structure of the class group. So this looks very weird if you're not used to Lean notation, but what we have here is just Z modulo 6 times Z modulo 2 being isomorphic to the class group of the ring of integers of K. That's what I'm saying. I'm just giving the structure as a group of the class group of this number field. And I have a proof that the class number equals 12. So so here is a polynomial, the polynomial that I told you about. And here is K defined as adjoining a root of this polynomial. And here are proofs of the invariance. So for example, I have a proof that the discriminant is equal to 7,000. And this, well, right now it looks very innocent. It's just 2 lines, but it actually relies on a bunch of other results. Here is a proof that the class number, for example, is 12. And then I can ask Lean to actually give me the axioms that this theorem relies on to see if I didn't cheat. Maybe I included an extra axiom and I didn't tell you, but I actually didn't. So you can see here that it says this theorem depends on the axioms, and you don't need to know what these axioms are, but these are the axioms that MATLAB uses freely. So it's like the axiom of choice, and then you have propositional extensionality and other stuff. So it's different from the Zermelo-Frankel set axioms, but we have dependent type theory plus some axioms. Okay, any questions so far? No? Yes.
Why is the choice of different axiom? I mean, if you put ZF axiom,
so you could, if you really want to work with ZF, you could define a model of ZF in dependent type theory, and then define there the axioms and work with that. But dependent type theory is the logical basis for Lean. So it already includes a lot of constructions that are involved in all parts of mathematics. And then we just need to add these extra 3 axioms to get full power.
So the argument is minimized.
Well,
because you need only 3, whereas the it's 5.
Well, the argument is not necessarily minimality, is that these are the axioms that we need in dependent type theory to make it work. Well, to make mathematics that we want to formalize work. But this is because of the system that is based on dependent type theory. You could, if you have systems that are based on set theory, you can have the set theory axioms. And you could, if you want, define a model of set theory inside dependent type theory.
But the expressiveness of the system. It's not necessary to have some theoretical minimal excellent basis that you want to easily, semi-easily do mathematics the way you would do it daily. But it's really about expressiveness. That's also why we care about dependent types. In principle, you could do this simple type theory, but dependent types is much more expressive than closer to how we are used to write.
So you could choose to work without the axiom of choice, for example, but then a lot of mathlib depends on that axiom, so you would not be able to use a lot of the mathlib results. And there are other projects that are integrating mathematical databases and Lean. So there was this project that they verified invariance of graphs in Lean. So there's a database called the House of Graphs. And in this project, they verified a bunch of invariants using Lean. And there's also a project to create an interface between Mathlib and the LMFDB, where you could have access to data that is in the LMFDB, but not necessarily formally proven. Actually, like the LMFDB doesn't have, well, it is not formally verified, right? So, Okay, now let me say something about automation that we have in Lean. So you already saw some of the automation that we have when you try the sim tactic or the ring tactic, where you didn't have to do things manually, right? And we have other symbolic methods already in Lean that can help us prove stuff without it being too painful. So, for example, if you have your statement involves a bunch of linear inequalities over the natural numbers or the integers, and your goal is also of this form, then we have tools that can help with that. So they are decision procedures for integer programming problems. So procedures for equalities and inequalities involving natural numbers and integers. I will show you an example. So let's see. If we look at this goal, we have a natural number n, and we have the hypothesis that 3 divides n, and n is less than 6, or n is bigger than 9, and n is less than 12. And I want to prove that this implies that n equals 0, or n equals 3. And I can use the tactic omega to solve this. So this can be done automatically. Similarly, it can handle stuff that involves minimum of two natural numbers, or the residue after dividing by a natural number. So if I have this goal, for example, I can prove that this implies y equals 5, again, by omega. And this, well, these are just linear inequalities. I can, again, prove this goal by omega. So for this sort of stuff, one doesn't need to struggle that much. We also have some automated theorem proving in Lean. So there's a tactic called ASOP. And what ASOP does is it knows some proof rules, and starting from your goal, it will try to apply some of these rules. And maybe when you apply some of these rules, you get new goals, right? So we saw already that when you use a tactic, you might get more goals. And you can try to apply different rules, and then you will get different goals. And then you get a tree of possible applications of rules. And then maybe one of these branches of the tree you can fully solve, and then you have a full proof in Lean. So it is based on exploring a search tree to find proofs. And ASOP can handle simple stuff. So this is, of course, very trivial example. So if you have propositions P and Q, and P implies Q, and you have a proof of P, you want to prove Q. We can, well, ASOP can do this. But this is, of course, very trivial. But maybe you have something like this. So you have a function from R to S. The function is injective. And you know that f of 1 equals 1, f of x equals 1. X equal to 1 implies y equals to 2 or y equals to 3. And y is different from 3. So then you can prove just by a chain of these implications and using the fact that the function is injective, that y is equal to 2. And actually, I'm just including this or y equals 5 just to make it slightly more complicated. So I can prove this sort of stuff with ASOP. You can do this automatically. And if I do ASOP question mark, I can see the proof. I can see the chain of applications. So I can see the branch of the tree that arrived to a proof. And recently, we also have Grind, which tries to put together different techniques in automated theorem proving. So what it does is, if you have a goal, it will negate the goal, and it will try to prove a contradiction. And it will do this by putting facts that it knows in like a bucket, and then trying to infer other facts using different techniques, such as e-matching and propagation of equalities and so on, to reach a contradiction and hopefully prove the statement. So here's an example of Grind, and this will be the last example set. Oh, and it has an algebraic solver. So if you have a goal like this, so in a commutative ring, you have all these hypotheses and you want to prove that they imply this thing, you don't need to do the calc stuff and yeah, the pain of manipulating these equations to get what you want. You can type grind and it does it for you. Another example where we can use grind is, well, I want to prove, for example, that if I have a function from the reals to the natural numbers, 4 times f evaluated at cosine of x plus sine of x squared is different for every x to 2 plus f of 2 times cosine of x plus sine of x plus 1. And well, what it can do is it can see that this thing, cosine of x plus sine of x squared, equals this thing if it knows the rules about cosine and sine. And once it sees that this is the same thing, it can use a solver of integer programming solver to check that this cannot happen. If you have 4 times n equals 2 plus n, this cannot happen in the natural numbers. So we can solve this goal automatically. Okay. And then this I won't show you, but we have tools that combine well, the symbolic methods with some machine learning methods. So there's something called the Lean hammer, which, well, in Isabel, there was already a sledgehammer. So Lean hammer is a version maybe of that. And the thing is, when you invoke an automatic theorem prover, so for example, this tree search, you want to give the prover the lemmas that are useful, the lemmas that it can use to prove the statement. So you have to select some lemmas. And this selection of lemmas can be done by a machine learning model. So you can train a model to, given a lean state, try to come up with a list of lemmas that could be useful for this automatic theorem proving. So this is how the Lean hammer works. And it's a combination of these two approaches of symbolic methods plus machine learning. And I already told you examples. So speaking of machine learning methods, some neural methods, models with neural networks are being used in different ways together with Lean and for formalization. So an example is auto-formalization. So we already saw that formalizing can be quite painful, and wouldn't it be nice to just have a LaTeX PDF, for example, and ask the computer to formalize it in Lean for you? So this is the dream maybe of some people, and there has been work towards auto-formalization. So large language models have been used for this goal, which is automatically translating natural language mathematics into a formal language. So an example of this happened in September 2025. So the Math Inc. company, or team, announced that their agent Gauss auto-formalized proof of the prime number theorem in Lean after 3 weeks of effort. So I will maybe briefly show the blueprint. So this blueprint, well, you can see that it contains so many lemmas. And this blueprint was created by human created. And the text was also human. And then they gave this to their AI agent, and it worked for 3 weeks, and it formalized the prime number theorem. However, it did require some human intervention during the formalization. So there were points in which it was stuck, and a human had to create maybe extra lemmas to help it continue with the auto-formalization. But it was able to do it. Now, if you look at the actual code, it does look quite different from what you would see in Mathlib, maybe. And it is using essentially structures that were already defined in Mathlib. So there's still, I would say, a long way to go to formalize maybe more sophisticated structures. So this contained 25,000 lines and more than 1,000 theorems and definitions. But it did require guidance and feedback from an expert. And finally, let me say something about automatic theorem proving using this combination of methods, of neural methods together with these formal methods. So as Sander mentioned, LLMs hallucinate, right? But Lean can provide the guardrails for these hallucinations because, well, everything is type checked in the system. So if you recall, in 2016, AlphaGo was able to beat one of the best Go players in the world. And it did this by training a model via a method called reinforcement learning, in which the computer played with itself thousands and thousands of times, and it learned, well, good strategies, and it was able to beat a human player. So sort of this philosophy is applied for the game of mathematics, where now Google DeepMind developed a system that is able to train itself to prove mathematical statements in Lean. So, well, let me describe briefly how it works. So they have a model that they train a model that given a Lean state, so the hypothesis and the goal that you want to prove, the model can give you suggestions of tactics to try next. And in this way, using this model that can give suggestions, they can explore a proof tree and maybe hopefully get to a proof. So, okay, so that is the model. And what they do is they start with a bunch. So they train the model with Mathlib, for example, but Mathlib is not enough. There is not enough formal mathematics to train a model of this magnitude. So what they did is they had some informal mathematics problems, and then they had a LLM that auto-formalized these problems into a bunch of smaller formal problems. Now, these formal problems do not need to exactly correspond to the informal version, because these formal problems are just going to be used for the model to play with. They don't have to correspond to the informal version. So now they had millions of formal problems, and now they use their model, their agent that can attempt to prove stuff, to try to prove these theorems, or either prove or disprove. And then if they are successful, they are then used to train the model and make it better. So the model is playing the game of mathematics and learning from playing that game and becoming better and better at proving. So, well, they used this for the International Math Olympiad in 2024, and I believe they were able to solve 3 out of 5 of the non-geometry problems. And then they used another system that they have specialized for geometry called alpha geometry to solve some of the geometry problems. And they achieved, well, they weren't really participants, but they achieved a silver medal in the 2024 International Math Olympiad. And there are other, well, companies and other people working on creating these sort of systems that combine neural methods with formal methods. Like, for example, Harmonics, Aristotle, also uses lean, and it was able to achieve a gold medal for the International Math Olympiad in 2025. Yeah, these are the different developments that might have big implications for the future of mathematics. The automated theorem proving, auto-formalization, or the large-scale collaborations.
Why are there so many companies involved?
Well, they want to show their model capabilities, and math is a good playground for doing that. So yeah, I would say that's the main incentive.
Like for example, math.
It's they're developing this Gauss system, and then harmonic is mathematical super intelligence. That's what they say. So yeah, I mean, yes.
For the IMO problems, would they do the questions under the competition?
No, they took way more time than the participants. Yeah, I don't recall exactly how much time or how much compute, but it was way more than.
And were they given the same problems in the same format?
No, they had to. My understanding is that they got the problems, the informal statements, and they manually, so a human, formalized the statements.
The statements were divided into problems. Like there is one of the problems is speed problem. I'm pretty sure about it.
So yeah, there was some human manipulation of the problems.
I'm not sure it's the hardest stuff because they have some older where interpreting human language to understand the problems well done. So I'm not sure it's really very different. I mean, it's so much harder to find the proof than to understand the way it's organized. For me, it's 2 years ago, I have read things about how to, for a computer program, when they have set it to the computer program context, the questions were the same as for the segment, and they understood perfectly what was the decisive and
So yes, that's all I wanted to say, and I'm happy to take any questions. Yes.
Yes. So about I talked about project or you can see there are some papers which are wrong in some results which are wrong, and sometimes I mean we know the results is wrong because there is a lemma where we are able to find a fiction code or example. The lemma, but that the sad truth is that we are not able to necessarily precisely where is the error.
Yeah.
So well, there are some experiments to use reading in order to get better knowledge of where there is a error or something like that. Yeah.
Well, when you are formalizing a proof in lean, you will definitely notice where the error is. So when people work in these big projects trying to formalize a big theorem like the ones you might be talking about, yes, the error, maybe if human mathematicians are not really aware where the problem is, they will become aware when they do the formalization process. Is that?
I understand that, but I was wondering if there were already some.
Oh, if this has happened.
Yes.
There was error in crystalline cohomology that was found recently. And yeah, the example that you
earlier on
mentioned.
there is in Lee and Isabel that this proof of this inequality of the home of really like that's the error, it's a crypto error.
Yeah.
Okay, but this is not okay. Yeah, but you were not aware that this was a new one. Yeah.
But you.
So in my example, I mean, it's way more subtle. I propose we really are happy. I know that maybe because we are lazy that we don't want to go step by step in the proof of schema or CC. So we even know that in a book there is a result which is contradictory with the result of the paper. And we know that the proof of the paper is correct.
Yeah.
And we are not able to understand which lemma, where in the book. I mean, there's something which is wrong, which implies it's a wrong result.
Yeah. Well, if one could try to detect that with the work of trying to formalize these results in the book, and sooner or later one will encounter where the error is.
There are already many projects with proof which relate to cohomology, particular cohomology or groups with some weird actions.
I know there is some group cohomology, but I don't know how many projects there are actively being done right now.
So a short question, something which was puzzling. Okay, you use several tools, but then how do you prove that the tools are correct?
Oh,
and
so how?
Solver, you use several categories of solvers, but how do you know that they are themselves correct?
Because if you use a solver, it will create a term in the language, in the logical language, which is the type theory. It will create a term, and this term is type checked. So it's checked to have the correct type. And this is done in the kernel of Lin. So you do need to trust something. Yes. You need to trust the kernel. But in principle, the kernel is small and can be inspected. But yeah, all these programs, all these tactics, they generate a term that is...
You understand, you get the checks, you have proof. The output, but you don't need to check what is.
Yeah,
exactly.
You give me that proof, but it's not formally proof that this solver is correct. But every time you output something, then the output is formally verified.
So use it to another level. Yeah, correct. I just need some replies.
Then again, by curiosity and maybe how grows the computing time with the depending on the problems that you give and how many structures that you have to check. So
yeah, there's a time limit that is set for the type checking. So maybe your proof requires a lot of unfolding definitions, and it will just time out. You can increase this time, but in principle, you try to structure your proofs in such a way that it doesn't take too long to type check.
But what is the impact of MATLib? Because MATLib is growing.
Yeah, but you don't need to. Yes, you can download the pre-compiled files, the pre-checked files. So every time you use a theorem in MATLib, you don't need to check everything down to the axioms. The partial results are already type checked.
Yeah, but okay, but the math, okay, let's say that maybe at some point, MATLib will have all the backing, maybe all algebraic geometry elements in it and everything, and all the stack projects in it. Okay, and how large it would be?
Very large.
You don't need, I mean, for example, what I know, you don't need to put all the environments. You create a special file and you put, I will use this one and this one. And I load in memory only the parts of math and that I suspect I will use.
Yeah. Okay, but then where is the repositories?
In GitHub. Yeah. There's one for MATLib. Yeah. And yeah, people are also they research about how to structure these big mathematical libraries. So this is a big question, especially as they increase in size.
Yeah. For example, this archive of formal proof, it's a group when you upload it each time, and at each time I upload from Isabel, and when you put the button bottom, you say, okay, this particular one I want to use something about
mixed state or projector or something like this. They put import quantum and then they will be able to put things without defining what's the measurement, what's the PFM, what's the state.
You want to write something?
Yeah, I just want to make a very quick remark. I mean, I guess everybody's hungry, so I don't know. Maybe there are still questions, but
Well, I can continue for a while, so.
well, we can answer questions over lunch, right? No, but I think that there was also well, a request that for a project for next week. I think that's well, we've seen, let's say, a little bit of lead, so it will be a bit too early to go for, let's say, formalize your favorite theorem. I mean, that's definitely a nice thing to do maybe later on. But I think, well, a natural project, if you want to do this next week, is simply to learn more lean. And then I can give two ideas. So you can go on with this a glimpse of lean, because we only did one fast track. So if you go here, then in the first file, I think that in the first file you see a URL to where this comes from. So then you can go to this glimpse of lean. You have multiple files of basics, and then later on you have multiple files of more advanced topics, also about the ring theory and stuff like that. Or maybe XOR. You go for this book, Mathematics in Lean. And so URL, I mean, if you Google it, you'll find probably immediately, but URL for this was in this preliminary PDF that was sent to you, how to install things. And probably if it all worked, you already have this. And this would be, let's say, the more advanced option. If you go through, the whole book or lots of the books, you will learn lots of, lean tactics, what's in MATLAB, and you have a much better understanding and the prerequisites here back to a more advanced lean project. Doing the whole book would be way too much for a week. So maybe optimistically, you maybe do chapters 2 up to 4. I mean, chapter 1 is just the introduction that you maybe already read. Okay, maybe 5. Let's be ambitious. Of course, it's better to understand than go fast. So if you actually do this, hey, you don't reach chapter 5. Of course, that's not a problem. Better understand chapters 2, 3, 4 very well than go to chapter 10 and do not understand.
Okay, then I have a question. So do you consider that it will be too much ambitious to have as project, let's say, some elementary results in homological algebra?
It will be way too ambitious to do that with the current league knowledge. I mean, it will be possible after you spend a few more weeks learning it, but you really need quite some basic. I mean, maybe Nicola can answer that.
I don't know. I mean, simple result from page 1.
It's just combinatorial definition is not hard, but we want to have like a categorical definition of the homological.
No, just
there is way.
You take the book of Tuan and
just
Find all the mistakes of one.
just and then try to formalize.
I know that the homological perturbation lemma, which I kind of half mentioned, that's but calc is something different there, but that's the people in Rubio, they have worked on doing that.
So I think that after knowing a bit more basics, that could be done. But I don't think that with the current knowledge you could already.
No, that was
aim
kind
for
of a
that.
PhD.
Yeah.
Problem.
Oh, no, I'm talking about. I'm talking about what Philippe is. Yeah.
Simple exercise that they can do in
Okay, so I guess we need a break, so we should thank Alain and Stanley for us. We'll start again at 2 o'clock.
Yes.
I was